All right, so welcome to dynamics. As the first problem we're going to work on in this dynamics class is this one. It's actually a statics problem. And the reason why I want to look at a statics problem is just to get back into the groove of solving mechanics problems again, but also to sort of highlight some things that we're going to be thinking about this semester, sort of in the context of a problem that you're probably more familiar with. So the problem is this. We have a ladder leaning up against the wall. The wall itself is at an angle relative to vertical, the angle of phi. The ladder is leaning at an angle theta relative to horizontal. The ladder has length L, and there's this dude on there, the construction worker, if you will. That worker has a weight W, and that construction worker is a distance D up from the bottom of the ladder. Up and to the right, I guess. The ladder has a roller that's leaning on the top end that's leaning against the wall. And there's a foot on the ladder, maybe a rubber foot down here. It doesn't look too detailed in my picture, but imagine there's a rubber foot there. And what I want to do is I want to find the force, the friction force on that rubber foot that keeps the ladder, prevents the ladder from sliding, right? So it's not sliding yet, so nothing's moving. It is a statics problem. It's something you should be familiar with. And again, I want to use this to sort of set the stage of what we'll be doing this semester. And the first thing is I want to introduce you to the way in which we solve problems in Mechanical Engineering 211. In a week or so, you'll get an official checklist, a way to solve problems in this class. But we'll go through the process here on this one. All right, so I've got a blank sheet of paper in front of me. Right here, I'm going to work on it as if I were working on a homework set. So hopefully it's something you can emulate yourself. The first order of business is to draw a picture of the problem. So I'm going to do that right here. I've got my straight edge. You don't have to have a straight edge to do your homework, but I highly recommend it. It makes drawings a little neater. So there's the floor and there's the wall. Got the ladder here. Here's the roller up at the top. It doesn't have to be a really fancy picture. I'm going to draw this dude on the ladder right there, like so. Again, nothing really fancy about my picture here. But on this drawing, what I want to do is I want to define quantities that are given to us. So, for example, this angle of the ladder was an angle theta relative to the horizontal. The wall itself was an angle. Put it in right here. It was phi relative to vertical. You'll recall I had some distances defined in the problem. So the ladder had a length right here. I'm going to call L. And there was a construction worker on the ladder, a distance D away from the bottom. And the construction worker had a weight W. So here I've defined all the relevant quantities in the problem. And when working on problems in this class, what I want to do at the very beginning of the problem, I want to list the quantities that are given to us. And I'm doing this explicitly, right? So things that are given to us. We're given the length of the ladder, the L. We're given D, the distance the person is up from the ladder. We're given the weight of that person. W might be 190 pounds. I'm not sure what that is, but W. We're given these angles, the theta and the phi. Anything else? I've got everything listed here, I think. So these are the quantities that are given, and I say quantities, but you might notice that there's no numbers here. And in this class, I'm going to give you very few numbers. We're not going to be working with numbers very much. We're going to be working with symbols most of the time. So that length is an L. L could be 5 meters. It could be 17 feet, it could be any length here you can imagine, right? I want to solve this problem generally. So when we get a solution, it'll work for any length that we have. And we can just, if we have a specific length of ladder, we can just plug that number into our solution and get the result, right? We'll solve this thing once and we'll have a solution that applies to a whole family of situations. All right, so the next thing I do when I solve a problem in this class, I list the quantity or quantities that I'm asked to find. Okay, so in this particular problem statement, we were asked to find the friction force at the foot that prevents sliding. So let me write that down here. Again, I'm very explicit about this. All right, now I've got that listed. Okay, so I think now we're ready to begin working on the problem. So why don't I ask you, what's the next step? Right, you've taken a statics course. Where do you go from here now that I've sort of set the problem up in terms of presentation on the page? Where do I go now if I'm going to analyze this problem? Think for a second. You should all know the answer to this question. All right, the answer is to draw a free body diagram. Yeah? So why don't you take a moment, pause the video, draw for me a free body diagram that's appropriate for this problem. All right, so at this moment you should have a free body diagram drawn already, and you're just going to use my discussion to see if we agree, okay? The first thing one should ask oneself when drawing a free body diagram is, well, free body diagram of what? Yeah, free body diagram of what? I'm going to draw a free body diagram of the ladder with the construction worker on it. So my free body diagram, you don't have, there's ways to do it differently, but one has to be kind of careful. But I think the simplest way to do it is there's the ladder, here's the guy on there, or woman, construction worker, could be woman. All right, so there's the ladder with the person on there. All right, now what goes on a free body diagram? In statics, the answer to this question is always very simple. The thing that goes on the free body diagram are forces, right? But in this class, it's not going to be as simple, or at least it's not going to seem to be as simple. It is going to be that simple, but it's not going to seem that way. On free body diagrams, we always draw forces, and that's it. You're going to be tempted, I imagine, a little later on to be drawing velocities on these free body diagrams or accelerations on the free body diagrams. No, only forces, right? And forces are things that are pushing and pulling on this body right here, the ladder and the person combined, right? So what are those forces? These are what should be on your free body diagram. So, first of all, this person, the construction worker, has a weight, and that weight goes straight down, right? Gravity's pulling on objects with mass. Gravity's pulling straight down towards the center of the Earth, right? This force does not come at an angle. Gravity always tugs straight down. I don't think I should have to mention it, but believe it or not, I kind of do. So I'm going to be thorough. All right, so there's a force acting on this system right here. When I have forces here, I like to label my forces. And we're going to be splitting forces up into components, as you might imagine, horizontal and vertical pieces. Maybe I'll put a coordinate system on here. Right, so horizontal, vertical right here, the horizontal direction, or the unit vector. For the horizontal direction, I'm going to call the I hat vector. And then I have the j hat vector pointing straight upward. There's my unit vector. So these are my basis vectors for writing vectors in this problem. So the weight is going to be this W right here. Weight is a force, by the way, right? This W right here is just a scalar. It's a number. It's what I say, 190 pounds earlier, right? It's just a number. So to make this thing a vector, I'm going to have to make this W in the j hat direction. Actually, it should be the minus j hat direction, since positive j hat is upward. So there's my vector. So all forces on free body diagrams are vectors, and they have to be labeled as vectors. So this says this vector is vertically downward, so I label it as a vector. There's my weight, W in the minus j hat direction. Cool. What other forces do I have on this object? The ground is pushing on the ladder, right?
Forces, again, are things that are pushing and pulling on my object. My object is my ladder with my construction worker on it. So when we're asking what the forces are, we're asking what things are pushing and pulling on the object. Typically, things that push and pull on the object are things that are in contact with the object. The exception is weight. It's a force that acts at a distance. So weight is not a contact force generally, but the other ones typically are. So we have the ladder coming in contact with the ground. In order to keep the ladder from penetrating through the ground, and in this case, also to keep it from sliding along the ground, I'm going to need a force from the ground acting on the ladder. And I'm going to split this force into pieces. I think you did it this way in statics too. We're going to write it as a horizontal piece and a vertical piece. And more importantly in this problem, we're going to write it in a component, a piece that's perpendicular to the surface, happens to be vertical, and a piece that's horizontal to the surface, that'll be your friction. Right? So let me put those forces in here. And you notice I like to use a straight edge here when I'm working on homework-like problems. It just makes the diagrams look so much neater, right? So right here we have a normal force from the ground pushing on the ladder, so I'm going to call this NG, and this is going to be in the positive j hat direction. And then we have a friction force. We don't really necessarily know which way the friction force is, but you might guess where it is. I'm going to draw it to the right. It seems to make the most sense to me. But static friction forces that are not sliding friction forces, they're the ones holding something in place. Static friction forces, the direction is usually determined by whatever direction is necessary to keep it from moving. You might guess that it's being pushing to the right. I think that's probably a good guess. But if I get the direction wrong, I should be able to fix it through the analysis. Okay, so there's the forces acting from the ground onto the ladder. All right, so what's next for my free body diagram? Again, we need more forces, right? We want to put all the forces on there. Are we finished? Well, no, right? We need some forces where? Up here. Up here where the ladder's in contact with the wall, right? The wall's pushing or pulling on the ladder. Right? It's providing a force to the ladder. So let me do that sort of similar to what we had before. Remember, the wall is at this angle phi, I guess. Right? And if I do something similar to what I did with the ground, I write this in terms of a component that's perpendicular to the wall, a normal force, and a piece that's tangent to the wall, right? So let me try that. So I think I've drawn, so here's my straight edge up here. There's tangent to the wall. So if I just sort of bring that down here, the force tangent to the wall would be sort of in this direction. Maybe it should be the opposite direction, but let me draw it this way. And then the piece perpendicular to the wall should be perpendicular to that. So let me draw it like so. So here's normal to the wall. And it's a vector, right? I'm not going to put it in the I hat, j hat direction just yet. I'll just indicate with an arrow above it to indicate that it's a vector, normal to the wall. And then here's friction force from the wall. How does that look? What do you think? Looking good? Looking good? Well, we got to think about this for a moment. Remember, it's not very well featured in my picture right here, but there's a roller right there. Actually, let's go look at the original problem. Where was it? It's over here. So here's the original problem. We were told that there's a roller up against that wall, right? Now, what does that roller do? Yeah, let's think about that. Think about what the roller's doing. In fact, I got myself, roller's just like a wheel, right? I got myself a little wheel right here. So let's think about the forces acting on this roller, which is at the top of the ladder. The normal force is going to be a force this way. Let's put it on there. Normal force is going to be a force perpendicular to the wall. It's going to be a force kind of in the direction I've shown, right? The tangential force, or the friction force, is going to be a force that way. Okay? Now, if I have a roller at the top of this ladder, so it's the roller that's in contact with the wall, then what's that friction force going to do? Ho, it's going to turn the wheel, right? It's going to turn the wheel. It's going to turn the roller. Right? But this is a statics problem. This roller is not spinning. Right? So there can't be a force tangent to the wall. Can't be a force tangent to the wall, or otherwise the wheel would start spinning. And that's what a roller does, is it removes that tangential component of the force, so that all you have left is the normal force, and the normal force acts through the center of the wheel, so it doesn't cause a rotation, right? It just pushes perpendicularly on that wheel. So what I need to do in this free body diagram is get rid of that friction force. Adios. Gone. It doesn't belong. What I have left is just the normal force from the wall. And maybe it's worth mentioning that when I'm working on homework problems like these, it's good to have a heavy-duty eraser available too. To get rid of all your mistakes. Pretend they weren't made. It's not perfectly erased, but it's gone, right? It's gone in our minds. Any other forces? Remember, forces are things that are pushing and pulling on the body. In this case, the body is the ladder with the construction worker on it. Let me just add a couple things. This is a free body diagram, so let's label it as such. We'll have other diagrams in this class, so we want to label our diagrams. So free body diagrams can be labeled FBD, which is the abbreviation for free body diagram. So I just realized something here. I think I realized is that we forgot a force, right? What about the weight of the ladder? Right? The construction worker has a weight, but the ladder also has a weight, right? The ladder, that weight should be pulling down. So we left that out. And you'll notice something in our givens. We weren't even actually given the weight of the ladder. What were we given? Let's go back and look at our problem real quick. Certainly there should be a weight of the ladder in there someplace. So here's our problem statement, and right here is where it talks about the weight of the ladder. It says that the ladder weighs much less than the construction worker. That's all it says about the ladder. So what I'm thinking, how I'm interpreting this, is that the ladder probably doesn't, the weight of the ladder probably, if this statement's true, the weight of the ladder does not contribute to the problem very much, right? You get this big, hefty, 190-pound construction worker on there. Maybe that's not so hefty, but solid individual. And the ladder may be a few pounds, let's say. It's probably more than just a few pounds, but nonetheless, I'm telling you that it's much less than the construction worker. So this statement in the problem statement is telling us essentially to forget about the weight of the ladder. It's not going to be important for us, right? Now, when we're working on a problem, we have to state that assumption explicitly. So what we're going to do is anytime we're making a non-trivial assumption, and neglecting the weight of the ladder here is not a trivial assumption, we're going to write it explicitly down here. So we're going to assume that we can neglect the weight of the ladder. So we're going to write that out here. For this particular problem, if we wanted to put the weight of the ladder in, it wouldn't be too difficult, but in this problem we're not given that weight, so let's not use it. All right, so what's next? What's next? Think for a second and then come back when you have an idea. So the next thing we're going to do is write equilibrium conditions for the system. And we're going to be explicit about that. So I'm writing equilibrium here, equilibrium conditions. And what are those conditions again? This is what you spent your whole semester doing in statics. Hoping you remember is that you're taking all these forces and you're adding them up to zero. So if you take all your forces,
sum them up. So that's what this sigma here means. You sum up all the forces, and that has to equal the 0 vector. I put a little vector over my 0 because each one of these forces is a vector itself. I take any number of vectors, add them together. Take 2 vectors, add them together, you get another vector, right? So the sum, if you want to be proper about it, this sum should be the 0 vector right there. Now my guess is you spent a whole semester of statics, and maybe after the first week, after doing some of the forces adding to 0 once, you probably this just became totally automatic to you. Add up all the forces, set it equal to 0. Okay, and it's easy for you to sort of forget why this is the case. Okay, and I want to bring this issue back up here because it's important for us this semester to think about where this comes from. And where this comes from is Newton's second law. Newton's second law says that the sum of all the forces equals mass times acceleration. Okay, so this is the foundational principle which determines our sum of the forces equals 0 thing. So sum of the forces generally does not equal 0. Generally, the sum of all forces will produce an acceleration. Again, in statics, nothing is moving. This ladder is stationary. There's no velocities, there's no accelerations. So the acceleration happens to be 0 in this problem. Okay, so this is Newton's second law, and in the very specific case where nothing's moving, the acceleration is 0, so that's why all the forces have to add up to 0. That's why all the forces have to balance out. Again, because things are not moving. In this semester in dynamics, we're going to put the right-hand side in. Okay? And if my experience teaching this class is any guide, a lot of you are going to just sort of instinctively, sort of gut feeling, not even thinking about it. You're going to just set forces equal to 0. But you don't do that in dynamics. That's what you did in statics. We're going to turn the page to dynamics in this class. So we will have accelerations, okay? But for now, since this is the first day, and we're reviewing or doing a review problem from statics, in this case, we are doing equilibrium conditions, so we will be setting the forces equal to 0. Okay, now when we set forces equal to 0, again, all these are vectors here. I think you found it last semester, or whenever you took your statics class. I think you found it convenient to split these forces into specific directions. Okay, you might be putting them in the horizontal and vertical directions. You might be putting them in directions perpendicular and parallel to something. It's easiest to solve these equilibrium conditions right here if you can split it into pieces and then get scalar equations out of them. Okay, and we're going to do the same thing here. We've got all our vectors, or at least the first 3 from the left side here. All 3 of these force vectors are either horizontal or vertical. So it makes, and just this one is the exception, the normal force in the wall. So it makes sense to put things into I hat and j hat components, which maybe is thinking ahead, and that's why I wrote this up here in the first place. So in order to sum all the forces in the horizontal direction, set those equal to 0, and do the same with the vertical direction, we're going to have to write all of our vectors into horizontal and vertical components. Again, the 3 on the left, already done for us. This one, we're going to have to think about this. All right, now this process of splitting a vector into components is called decomposition. And you may recognize, I hope you recognize that I've already asked you to do some vector decomposition problems for practice, because this becomes a really good skill to have if you can do it quickly. We'll do it a little bit slowly for now. So what we do is we take this vector, in this case it's a vector going this way, right? And we want to split it into horizontal and vertical pieces. So what we want to do is write this vector right here as a vector sum, a sum of a vector this way plus a vector this way.
Yeah, so here's the original NW, normal force from the wall. And I want to write it a piece this way and a piece that way. Right? The right angle here goes between the component vectors. Cool. So the way to decompose this thing is really a matter of writing this force triangle right here. And I guess you have to label one of these angles here. Anything known here? Well, you might recall that, well, let me put it right here. We're given this angle phi right there, right? There's that angle phi that's given to us. So, I guess you would say this angle phi, this angle right here is angle phi, which would make this angle right here angle phi. Work out the geometry yourself, if you will. That angle right there is phi. So therefore, if we're to decompose the vector NW, normal force to the wall, how much would be in the horizontal direction? This would be NW. This would be the adjacent side of the triangle, right? This is the side that's adjacent to the angle. So that would be a cosine phi in the I hat direction. And the other side, the vertical piece, is opposite of the angle. So that's why we have a sine there. So plus NW sine phi. That's in the j hat direction. Yeah, how's that looking? Make sense? Actually, there's a little problem with it. Do you see the problem? Right? NW here is a scalar, right? That's the magnitude of that vector. And it's got a piece, at least I've drawn it, it's got a piece upward and a piece to the left. The piece to the left is in the minus I hat direction. So if NW is a positive number, I should have a minus sign right there to get the direction right. Cool. All right, so this vector, this normal force from the wall, has been decomposed. All right, so now all I have to do is write the equilibrium condition in terms of its horizontal and vertical components. Now, if I've drawn a free body diagram, well, then this next part should be almost trivial. So this is why drawing the free body diagram is so important. It sort of sets up the rest of the analysis. So let's go ahead. We'll pull off the I hat component, the horizontal component. Right, each one of these vectors has the I hat or a j hat component, so all I'm doing here is I'm filtering out the I hat piece. So this is my notation here. I just say I hat colon. So then I write the I hat pieces right here. So I've got, just looking at my free body diagram with my labels on the vectors, I've got Fg in the I hat direction. This is the friction force from the ground. In fact, this is what we're after, right? This is the unknown. And then my normal force from the wall, it also has an I hat piece. So I'll say minus NW cosine of phi, and that gets the I hat. I don't write the I hat here and the I hat there. I'm filtering out the I hat piece. What I have is a scalar equation here, right? Here are the horizontal components that have to add up to 0. Right? And then I do the same thing for the j hat direction. I got the normal force from the ground. I've got weight, so minus W in the j hat. And then I also have a NW sine phi. And that has to add up to 0. Cool, so there are my equilibrium conditions as I have them so far. So let's think about this. Where are we going with this? So once we get the equations, in this case the equations of equilibrium, but in the near future it's going to be equations of motion, we've got to think about where we're going with this, right? Where are we going? What we want to do is find the friction force. This friction force, that's the Fg right there. Right, that's what we're looking for. So we're looking for this one, right? We want to find Fg in terms of what? We want to find it in terms, well, I guess I'll say it this way. Right now, I could, if I wanted to, I can just say Fg is equal to NW cosine phi, right? And there you might say, oops, this is N sub, It's not N times the weight, it's normal force of the wall. So subscript W, sorry about that. So I can write Fg equals NW cosine phi, and you can say, hey, there's my answer. That's what I was looking for. I'm looking for an expression with this Fg in there. But hold on. What I want to do is I want to write this in terms of things that I know. Right? The things that are given to us are the length, this distance from the bottom of the ladder, the weight, the angles. Right? These are the things I know. I have no idea what NW is, right? So, this is what you do when you put numbers in there too, right? You keep on solving until you just have a number. But in this case, we're not doing numbers. We have to keep on solving until we have our answer. In this case, our answer is Fg. We keep on solving until we have Fg in terms of things that are given to us, right? And this is why we write the list of givens. Right? We compare these symbols right here to the symbols right here, and we'll notice that NW is not on my list of givens. I have no idea what the wall normal force is. If I did know the wall normal force, then that'd be done now, but I don't. So this doesn't end it for me. I guess I'll say it that way. Okay? So if I know what NW is, then I can be there. So look at the next equation. It has an NW in there. But notice it also has an NG. So this NW equation, the second equation right here, has NW. It has a sine phi. Phi is known. W is known, right? It's on my list right here. There's phi. There's W. But NG, the normal force on the ground, is not known. Ooh, crap. So I can't use the second equation, at least not directly, to substitute it in here and get the Fg. I'm not there yet. Yeah, these equations by themselves, these two equations are not going to do it for me. Do you see that? Doing the substitution, it's not going to work. And you can kind of see it too. If we do a counting of unknowns, right, the unknowns here, the unknowns are Fg, NW, and Ng. Right? There's 3 unknowns. And there's just 2 equations. Uh-oh. We don't have enough equations to solve for our unknowns. Our system is underdetermined. So we're going to need another equation. What do you think? Can you think of the other equation? Well, one suggestion might be to put our sort of Coulomb friction model in. So another equation, let's say it this way, Fg, that's a friction force, right? What kind of friction is this? It's static friction. It's static friction because it's not sliding. It's just sitting there planted on the ground. So that static friction is going to be mu s times the normal force here, mu s times Ng. What do you think? That gives us another equation, right? But there's a problem with this. In fact, there's 2 problems with this. One problem is that I don't know mu s. It's not given. It's not given to us. So this is not working for me. But a more fundamental problem is this is not how static friction works. Right? Static friction is not equal to mu s times Ng. We're going to be talking about this more in this class. But the static friction is really an inequality type thing. The static friction says that friction force has to be less than or equal to mu s Ng. So this is not going to tell us what the static friction, if I did know what mu s is, it's not going to tell me what the friction force is. It's going to tell me what the friction force can't be, essentially. Right? So this is not going to work for us. So pull out the jumbo eraser again. All right, so that doesn't work. So let me ask you to think about it for a moment. Again, got to be thinking, always thinking.
Where am I going to get another equation? How am I going to do this? Where am I going to get another piece of sort of physics to tie this thing down? All right, take a minute. Once you have some thoughts, come back and we'll work on it more. All right, so how are we going to proceed? Well, I hope you realized or remembered that the equilibrium conditions is not only, or at least in general, does not only include some of the forces adding up to zero, but also there's a condition with the moments, right? What do moments tell us? Moments, so I've got all the forces acting on this object. Here's the object right there in the diagram. So I've got this ladder. I've got some forces down here, forces there, and a weight in the middle. And if all the forces, if all the moments did not add up to zero, this thing would start rotating, right? I got some forces down here and some forces up there. They might not balance out, at least if this was not in equilibrium, they might not balance out, and you might get a rotation right here, right? That's what moments do. They cause things to rotate, right? A moment is a sort of a twist type action. Right? And I need all the twists to add up to zero so the thing does not rotate. Right? So let's add that to our equilibrium conditions. So we're summing up all the moments and setting that to zero. Moments are vectors as well. So that's why the arrow is over the pieces here. So let's do it. So when we set up moments, we have to choose a place to take moments about. That's another thing we did in statics, right? Where do you want to take moments about? In principle, we can take moments about any place. I can take moments about right here. I can take moments down here, up there, about the person. I can even take moments about points that are not on the body itself, right? I've got almost complete choice to decide where I want to take moments about. So do you have a good suggestion on where to take moments about? You know, sometimes some choices are a little more intelligent than others, or at least make things a little easier than other choices. Is there a place to take moments about where things become easy? I think so. So look at these are my forces again. Which forces are known? Which ones are unknown? I know the weight, right? I know the weight. I know this W that's given to me. Where is it? There it's given. But I don't know the friction force. I want to know that one. I don't know the normal force. I don't know the normal force from the wall. This is normal force from the ground down here, normal force. So I don't know these three forces. So if I write a moment about some arbitrary point, all three forces are going to contribute to the moment. And in principle, that's no big deal, but I'm going to have to start solving equations with all three unknowns in there. Right? Three unknowns. Boom, boom, boom. But if I were to take moments about this point right here, both the friction force from the ground and the normal force from the ground act through that point. I had my wheel. I forgot my wheel. My wheel. Right? And for this wheel, the center axle is fixed. So if I have a force that acts through the center axle, that does not produce a moment, right? Because that does, this would produce a moment, but this does not produce a moment, right? Because this force coming from my finger here acts through that center, right? So likewise, if I take moments about this contact point with the ground, let's give a contact point a name. Let's call it P, point. If I take moments about this contact point P, this acts through point P, that acts through point P, no moment about point P. What produces a moment? Ooh, my weight produces a moment, but I know what the weight is. Ooh, that's an unknown. That's a known, so it produces a known moment. And then this thing produces another moment, and the moment from this one would have to balance that one, and we just have one unknown that we can solve for, the NW, right away. And if I know what NW is, ooh, I can get that friction force on the ground. So this is looking like a good way to do this. Let me put down my wheel so I can think about this. So
what I'm going to do is take moments about point P. The moments are going to be moments counterclockwise or clockwise, and I hope you remember from statics, those moments are vectors, and these vectors, or these moments, are in the plane here, so the actual moment vector is going to be out of the plane, or in the k-hat direction. We've got a right-handed coordinate system. I cross j would be k, so k would be out of the screen. So the way I write this is I'm going to do moment equation to indicate there's a moment equation. We're going to take moment equation. We're going to look at stuff going on in the k-hat direction for the moments. So I'll say k-hat here. And we're taking moments about point P. So I'll put the little subscript P here. And then I'll have this thing right here to indicate we got a moment going on. That twisty action right there. That's my notation. Okay, so my moment equation, kp hat direction, is going to be what? Well, as I said, these two forces do not contribute to the moment. And we'll start with the weight. So the weight produces a moment. So moment is a force times the distance. So what do you think about this? So actually that's going to produce a moment. The weight is going to produce a moment that way, right? Into the page, that's in the minus direction. So I'm calling this way, counterclockwise moments, positive. Right, this little arrow indicates my positive direction. It'll be in the kp direction, positive. So this one's going to produce a negative moment. So how about minus w, and that's the force, and then the distance is d. So how about this for the moment due to the weight? W times d. Sound good? Got to be careful. Got to be careful. This is not right. Do you see that it's not right? Because the offset from point P right here would be this distance right there. That distance is d. But this direction, how do I do this? Let's see, here's the direction of the point where the weight is acting from D, and the weight is acting straight down, right? So this weight and this, it's really a position vector, those two vectors are not perpendicular to each other. Yeah, so it's not just W times D. What you have to do is look at the perpendicular component of this thing. So if I were to just draw a line right here, the perpendicular distance from point P would be that distance right there, right? This distance, not that distance. The perpendicular distance, the one that goes into the moment calculations, that distance, right? If this distance right here is d, then this one is d times cosine of the angle right here. Right? That's probably a better way to look at it up here. Right? So here's a distance d. This distance right here would be d cosine theta. So what we have is WD cosine theta as the moment coming from the weight, right? Negative because it's producing a clockwise moment, and we're calling counterclockwise positive. So there's the moment due to the weight. And then I've got a normal force due to this, I got a moment due to this normal force, right? And how do you calculate that? Well, one way to do it, I'm going to sort of scratch in my free body diagram right here, but I'll erase it in a moment. So one way to think about this is we've got a normal force that can be written as two components, right? Vertical components, that's the NW sine phi. That's the vertical component. And a horizontal component, which is the minus NW cosine phi. Right? So I can take this thing and split it into two pieces. So let's do one piece at a time. Let's do the vertical piece.
So the vertical piece is going to produce a moment. The force, the vertical component of the weight is NW sine phi. Oh, wait a second. This vertical piece is going to produce a clockwise moment, right? Oh. So this is going to be plus right here. And then I've got NW sine phi. That's the force. And then I need the perpendicular distance. Right? The perpendicular distance is this distance right there. So that's L, the length of the ladder, times cosine phi. Times L cosine theta. Not phi, theta. Theta is this angle down here, right? Theta. Right? So there's your moment due to the vertical component of the normal force. Now the horizontal component of the normal force is going to produce another positive moment, right? So plus, and the force is going to have magnitude NW cosine phi, right? That's what that is. That's what that's telling us. And then the perpendicular distance is going to be this height right there, right? It's going to be this distance right here, which is L times sine of the theta. Woo! So there's my three components of the moment. All those have to add up to 0. The three constituent pieces of the moment, they're all the same component, I guess. They're all in the k-hat direction. So now I have three equations for my three unknowns. Like it. So in terms of solving these equations, where does this leave me? It leaves me in a pretty good place. Remember we talked about it when we were discussing where to take moments about. Actually, let me sort of get rid of this stuff right here because these things really don't belong on a free body diagram. It's just for illustrative purposes I put it in there. All right, so remember when we were talking about taking moments, we chose to take moments about here because that would leave just one unknown. And that's exactly what we see in our equations, right? W is known, D is known, theta is known, right? The only thing, L is known. The only thing that's not known in this equation right here is the NW, right? So we can solve for that one right now. We can say NW is equal to, let's say, we'll put the WD cosine theta on the other side. So this be, and then NW has this piece in it and that piece in it. So what you'd be doing is you'd be dividing by what, L. Both these things have an L in it, right? L. Yeah, check my work here. Make sure I'm doing this correctly. I'm prone to make mistakes occasionally. At this time, I think I'm okay. But again, you should be checking this. All right, so there's the NW. And then what am I after again? What I'm after is the FG. FG in terms of NW, ooh, it's right here. Let me call this one equation number 1. So I'll say, I want to substitute in equation 1. Substitute into equation 1. Then we find that FG is equal to, well, it's this whole thing just multiplied by cosine phi, right? So check out where we are. Check this thing out. This is interesting, right? What we want is an expression for FG. Oh, we have an expression for FG, right? Actually, we had an expression for FG earlier. This one wasn't good because I didn't know what the NW was. I knew when I come up with an answer, when I come up with FG, the thing that I want to determine, I need to be able to write it in terms of, only in terms of things that are given. Let's look at this FG. What do we got? I got W, I got D, I got L, I got sine and cosine of phi and theta, right? Look at this. Look at this. Look at this. Look at this. Here's W. Here's D. Here's L. Here's theta and phi. Right? All these things are given to us, and these are all the things in my answer right here.
My answer contains terms only, I'll say it this way. My answer only contains terms that are given. Guess what? Now I finally got an answer. And when I have an answer and I'm feeling good about it, I'm not sure I'm feeling really good about it yet, but nonetheless, we can make ourselves feel a little better in just a moment, maybe. Check it out. I got an answer. I put a box around it. Okay, this is what we're going to do in this semester. Why do we put a box around your answer? Because when you're working on this stuff with symbolically, you'll have lots of expressions here and there. Here's an FG equals something expression right there. But here's the one that's our answer. And we put a box on it around it to indicate to say, this is it. This is the one. This is the thing that you asked me to find. It's right there. We're looking good. What do you think? Cool? Actually, I like this. But before we say we're done, I want to do one more thing. I want to check the dimensions. What do I mean by that? Well, what am I after? I'm after FG. FG is a force. And I have FG written in terms of lots of different quantities here. Not all these things up here, the givens are, not all of them are forces. In fact, this one's a length, that one's a length, that one's a force. This is a, what's that? Radians, degrees? I don't know. Right? But here I have an answer. Where is it? Here I have an answer in terms of things given. So I've got this big alphabet soup on the right-hand side. If this thing is going to make sense, then this alphabet soup on the right-hand side, that better have dimensions of force. Right? This thing better be a force. Right? I can't say, if I were to put numbers in there, I can't say the friction force is equals 3 meters times cosine theta. Because that would be meters, right? This thing better be, this thing on the right-hand side better be force. Right? So what we like to do, or what I'm going to require you to do when you come up with an answer, is check that the dimensions make sense. When I say dimensions, I mean the sort of units that you use to represent this thing. Right? So we said that FG already, that's a force. Let's look on the right-hand side. This is where the alphabet soup is. So what we have here is W. W is a weight. How do you measure weight? In terms of newtons or pounds, right? Or tons, right? W is also a force. That's the amount of push or pull. So this would be a force right here, the W. D right here is what? D is the distance up the ladder, along the ladder. That's a length, right? So I've got a force times a length. Ooh, that's what I got in the first part of the numerator. Then I have a cosine theta. What the heck is a cosine theta? Well, let's look at this problem over here. Oops, look it up here. Here's a cosine theta. Actually, let me just draw this triangle in that I had before. Cosine theta is what? It's the, if I were to draw this little triangle right here, cosine theta would be this length of the triangle divided by the hypotenuse. That's cosine. So cosine theta is a length divided by a length. Ooh. So cosine theta is dimensionless. It's just a ratio of two lengths. It's just a number, right? Similarly for cosine phi, that's a length divided by a length. Right here, it just happens to be a different triangle. But cosine phi would be this length divided by a hypotenuse, right? That's the length divided by a length. Whenever we see a cosine or a sine of an angle, cosine angle, sine angle, cosine angle, whatever, those are just dimensionless quantities, right? They're just a ratio of lengths. So in terms of checking our dimensions, we can just sort of ignore them because they don't change the dimensions of the problem. Okay, so let's look at the denominator now. What we have here is a length. This length happens to be called L. Maybe I wasn't too fortunate with this notation here, but nonetheless it's a length, right? And then this sine, cosine, plus cosine, sine, again, that's dimensionless. So what we have on the right-hand side is a force times a length divided by a length, which is a force, which is exactly what we want. Ah, isn't that nice? Isn't that satisfying? If the units didn't turn out right, the dimensions didn't turn out right, then we would have a problem. That means we did something wrong. We need equalities to make sense. Here's an equal sign. Equal sign means this thing on the left has to be the same thing as this thing on the right. To do that, they have to have the same dimensions. You can't have 32 pounds equals 4 feet, right? It doesn't make sense, right? And in this case, there is consistency dimension-wise. So we're happy with this, and at least we're happy with it dimensionally, and I'm feeling more confident about my solution now. All right, the dimension won't catch all your mistakes, but it'll certainly catch some of them. All right, so I consider this problem done. We're done. Actually, there's one more thing. I'll have you think about it. I'm not going to do it. Something for you to think about. Does this answer make sense? Does this answer make sense? Again, it's just alphabet salad, right? This is alphabet soup. Before now, it's alphabet salad. It's just a bunch of symbols, but this should have meaning here, right? And in particular, one thing that catches my eye when I'm checking if things make sense, look at this denominator. Taking something, I'm dividing by something else. This thing I'm dividing by, the denominator, it better not be 0, right? If it were 0, we'd be in a world of trouble. It means we'd get an infinite force out of this thing, right? Divide by 0, you get infinity. Can this thing ever be 0? Can you choose some reasonable values of theta and phi and get this answer to be 0 in the denominator? If so, then we got a problem, right? We'd have sort of a regular looking sort of ladder leaning against a regular seeming wall, right? And the answer we'd get would tell us that we'd get an infinite force out of that. If that were true, wouldn't we have an amazing device? I don't know. Or a very unstable device, or a very unstable ladder in this case. Well, let's just think about that, okay? These are things that you should be thinking about when you're working symbolically. Does your answer in the end, not only does it have the right dimensions, does it make sense? Okay, I'll have you ponder that one, because it's actually sort of interesting geometrically what's going on with that. All right? So I consider ourselves finished with this problem. Over and out.